Welcome to the Crazy Hat Chemist. So here we go. We're going to be talking about the third video in a series of 5 about chemical reactions. Today we're going to be talking about balancing chemical equations. This is going to be part A. So here we go. Bam! The sequence of balancing is going to be the following. You're going to start off with the most complex compound. That is the compound with the most unusual elements and the most numerous of them. And then you're going to work your way down to the least complex compounds. Okay. For a combustion reaction, you always balance them in the following order. And this was already discussed in a previous lecture. Number 1, you're going to start off with carbons. Number 2, you're going to start off with hydrogens. And then finally, you're going to end with oxygen, and that is going to be the diatomic element. You're going to always balance diatomic elements the last, even if they're not combustion reactions. And the beautiful thing about this whole entire balancing chemical equations is you can check your work at the end and know that you got the right answer. That's a fantastic thing. So the final step in all of these is to verify that you have done the correct balancing of that chemical equation. So here we go. Let's start off with the first one, balancing chemical equations number 1. You're first going to, so it says, write a balanced equation for the reaction between magnesium metal when burned in air. So, magnesium metal, that it says that it's a metal, so that tells you that it's elemental magnesium. What is the state of matter of elemental magnesium? That's right, it's a solid. Okay, and when it's burned in air, what's the major component of air that's most important? It's not nitrogen gas, it is oxygen gas. So we're going to have magnesium metal and oxygen. Okay, so we got magnesium metal, that's a solid, oxygen gas, and then we got to figure out what type of reaction it is. So in magnesium metal and the other reactant is oxygen gas, there are no Californias. Therefore, this is not either a single displacement or a double displacement. There's not one compound, so it's not a decomposition reaction. It's not truly a combustion reaction in the form that we're used to, and that's carbons, hydrogens, or carbons, hydrogens, and oxygens, plus molecular oxygen. I realize that there is the molecular oxygen, but the magnesium is different than carbons and hydrogens. So it doesn't fall within the combustion pattern. So therefore, we only have one other reaction type, and that is a combination type. So what we're going to do is we're going to look on the periodic table for the periodic trend charges of these two elements. That's magnesium and oxygen. Magnesium is a group 2, so therefore it's a 2+ charge. And oxygen is oxide ion, and that's a -2. We're going to take the 2+ for magnesium. We're going to take the 2- for oxide ion. We're going to take those two numbers right there. The 2 for the magnesium, the 2 for the oxide. We're going to take the bull by the horns. We're going to take the absolute value of those two numbers, flip them, and bring them down, and we're going to write down the formula. And that's Mg2O2, and then we do have to reduce it. And this is what you get. MgO, because it's a 1-to-1 ratio, and that is a solid. Now we're going to start balancing. Now we have an unbalanced chemical reaction with reactants and products. So we're going to start off with the most complicated compound, and that is the product, which is magnesium oxide. That's the MgO. There's one magnesium on the product side. How many magnesium on the reactant side? There's one. So the magnesiums are balanced. We're going to go back to the product side in magnesium oxide. How many oxygens on the product side? There's 1. How many oxygens on the reactant side? There's 2. The magnesiums are unbalanced. So a really simple way is to place a 2 in front of the magnesium oxide, and then again, you're going to place a 2 in front of the magnesium. So we're going to do that in sequence here. And this is actually the balanced chemical equation. There's a delta above the arrow because heat is necessary to make this reaction proceed forward, like light a match or put the magnesium in a Bunsen burner or something like that. Okay, I'm going to give you an alternate path for balancing this equation, and this also works. So I'm going to go back to reaction number 2, and I'm going to say that I have the magnesiums are balanced and the oxygens are not. I need to get 1 less oxygen on the reactant side where it is in the diatomic state. So I'm going to put a fractional coefficient in front of the oxygen. And here's what I get. So this equation here is now balanced. Now what I'm going to do is I'm going to get rid of the fractional coefficient in front of the oxygen, and I'm going to multiply the entire equation by 2, and then I get that bottom equation. So there's only one way that you get the balanced equation. There's only one correct balanced equation with whole number stoichiometric coefficients. All right, hopefully you got that one. So let's go on to balancing equations number 2, hopefully. All right, hold on just a second, Bo. You are baking me crazy. So this is elemental humor. Hopefully you get that. Okay, reaction number 2. Write a balanced equation when methane, that's CH4, completely burns. Methane is natural gas. That's the gas that you have in your chemistry lab when you light a Bunsen burner. So methane, CH4, when it burns, that tells you what is the component to air that burns. Just like on the previous example, it's not nitrogen, which is the major component to air, but it is the oxygen. So we're going to have methane, that's CH4, that's in the gaseous state, and a molecular oxygen, that's O2. Okay, and that's also in the gaseous state. This follows a particular type of reaction. This type of reaction is a combustion type of reaction. Okay, so all combustion type of reactions have the same set of products when they're carbons and hydrogens on the reactant side, of which this is that case. So what are the products for a combustion reaction? Always, it's the simplest type of reaction to write the products for. That is carbon dioxide and water. So now I have an unbalanced chemical equation right now. So when we're balancing combustion reactions, you always balance it in this order. That is carbons first, hydrogen second, oxygens, the diatomic at the end. So I'm going to balance the carbons first. How many carbons on the reactant side? 1. How many carbons on the product side? 1. The carbons are already balanced. So now what I'm going to do is go to the hydrogens. How many hydrogens are on the reactant side? CH4, there's 4 hydrogens on the reactant side. How many hydrogens are on the product side? There's 2 in H2O. So you can only write stoichiometric coefficients as numbers in front of the formula. So I'm going to put a 2 in front of the water. And that's what I get right here. So now I have the carbons balanced, I have the hydrogens balanced, and now I'm going to look at the oxygens. So I need to figure out how many oxygens are on my product side. So I'm going to look and find out how many oxygens are in carbon dioxide. There's 2 oxygens in carbon dioxide. And then I'm going to look at how many oxygens in water. But I do need to include that 2 stoichiometric coefficient that is there. That 2 distributes with the whole entire formula of water. So there's 2 times 2 hydrogens, that's 4 hydrogens, and then there's 2 times 1 oxygen, so there's 2 oxygens. Then I'm going to add these 2 numbers up right here, and I get a total of 4 oxygens on the product side. Now I'm going to find out how many oxygens I have on the reactant side. I have 2. And I want 4. So I'm going to place a 2 stoichiometric coefficient in front of the oxygen. And now I have my balanced chemical equation. Again, this is a combustion reaction. It requires some input of energy to proceed forward. Therefore, that delta on the above the arrow. All right, hopefully that worked for you too. That was equation number 2. Let's carry on. Here's a chemistry pickup line, just in case if you need one someday, and I'm betting you probably will need one. So, you look familiar. Did we take class together? I could have sworn we had chemistry. Okay, balancing equation number 3. You're going to write a balanced equation when potassium chlorate is heated in a crucible in the absence of air. There's a key word there, and that's absence. That tells you that there's no other reactant. Okay, so key into those words there. So, potassium chlorate. Potassium is a group 1 metal, so therefore its periodic trend charge is a +1. Okay, and then chlorate. That's different than chloride. That is a halide ion. Chlorate. So hopefully you remember these polyatomic ions. That's hypochlorite, chlorite, chlorate, of which this is, and hyper or perchlorate. This is chlorate. That's ClO3 with a 1- charge. So I'm going to take the 1+ on the potassium, the 1- on the chlorate. I'm going to take the absolute value of those 2 numbers, take the bull by the horns, flip, bring it down, and I got my formula. And I don't write 1s. So it's KClO3. Okay, and now I'm going to put that delta above the arrow because this also, it says that you're heating it. So you're going to heat it in a crucible. This requires heat and energy. So this is what type of reaction? There's only one reactant, so it's a really easy type of reaction to identify. There is only one type that this can be, and that is a decomposition type of reaction. Okay, on all decomposition type of reactions, you end up with a particular set of products, and that is you get a gas as one of the products, and you can only see, hopefully here, that you can only potentially get two different gases. That is chlorine gas or oxygen gas. And I said in a previous lecture, the gases that you're most typically going to get is oxygen gas, carbon dioxide gas, or sulfur dioxide gas. Chlorine is not one of those, so the oxygen gas is going to be the one that you're looking for. And then the other product is going to be either a California, that's a cation and an anion combined together in the appropriate charge ratio, or an element. And if I remove just the oxygen as oxygen gas, that's O2, then I somehow still have to deal with the potassium and the chlorine, so I'm going to put those together. And so that's what this Ca, that California, and that element plus a gas is. So hopefully that makes sense. So I'm going to combine the potassium together with the chloride ion, and I'm going to take the bull by the horns. That's a 1 plus and a 1 minus. I'm going to take the absolute value of those numbers, flip the numbers, bring them down, and I'm going to get KCl. Okay, so hopefully you've done this reaction in the lab. It's a very common reaction in chemistry labs. And that's heating up potassium chlorate. You get potassium chloride, which is a white powdery solid there, and you remove the oxygen gas. I want you to make sure that you see that this unbalanced equation is not balanced, although I did write the correct formulas. That's why it's O2 gas. It's not O3 gas. It's not ozone. We're not getting ozone out of this thing. So now what we're going to do is we're going to look at the most complicated formula. That's the reactant, that's the potassium chlorate. And we're going to figure out from there and start balancing. So on the reactant side, I have 1 potassium. On the product side, I have 1 potassium. So the potassiums are already balanced. On the reactant side, I have 1 chlorine. And on the product side, I have 1 chlorine. So the chlorines are already balanced. And then on the reactant side, I have 3 oxygens. And on the product side, I have 2 oxygens. So the oxygens are unbalanced. So what's the greatest common factor between 3 and 2? That's a 6. So I need 6 oxygens on both the reactant and product side. So I'm going to put a stoichiometric coefficient in front of the potassium chlorate of a 2, and that will give me 6 oxygens. And I'm going to put a stoichiometric coefficient in front of the oxygen that's on the product side of a 3, and that will give me 6 oxygens. And that will lead me to this step right here. So what is unbalanced now, that was balanced previously, was the potassiums and the chlorines. And so now I need to do that, and that should be a simple 2 stoichiometric coefficient in front of the potassium chloride. And that is my balanced chemical equation. And again, like on the previous problem, I'm going to show you an alternate path, and this is step number 3.5. Okay, you should see that on step number 3, so if you look at step number 3 again, the potassiums and the chlorines are already balanced. What we're going to do is put a fractional coefficient in front of the diatomic, that's the oxygen gas. And I want to get 3 oxygens on the product side. So I'm going to multiply by 3/2, and that's what I get right there. So now I'm going to, this equation, 3.5, is actually already balanced. So you're going to have to check with your instructor and see if fractional coefficients are okay. I'm going to say no. I'm going to say I need whole number stoichiometric coefficients. So what you're going to do with equation 3.5 is multiply equation 3.5 by 2, and then you're going to get that bottom answer just like you did before. Fantastic. All right, that's that one. Okay, the next one. If that didn't work as far as a pickup line, maybe you should try this as a pickup line. You must be made of copper and tellurium because you are so cute. All right, fantastic. That's another one. All right, so I am the Crazy Hat Chemist, and that was balancing equations, reactions, part A. And we're going to actually do a part B of this one too, because we have 2 more reactions to do. I'll see you later.